31st of December 2023. Transformer-based large language models have become a fixture in modern machine learning. Correspondingly, significant resources are allocated towards research that aims to further advance this technology, typically resulting in models of increasing size that are trained on increasing amounts of data. This work, however, demonstrates the surprising result that it is often possible to significantly improve the performance of LLMs by selectively removing higher-order components of their weight matrices. This simple intervention, which we call layer-selective rank reduction, LASER, can be done on a model after training has been completed and requires no additional parameters or data. We show extensive experiments demonstrating the generality of the finding across language models and datasets, and provide in-depth analysis offering insights into both when LASER is effective and the mechanism by which it operates. There's a code and website, so that's a good idea. Hopefully the code is actually there. Introduction. Since their original release, transformer-based LLMs have been shown to be remarkably proficient on a wide array of important machine learning tasks. Their underlying transformer architecture has become state-of-the-art for modeling and reasoning about natural language and has shown promise in domains such as computer vision and reinforcement learning as well. Contemporary instantiations of transformer architectures are infinitely large, requiring tremendous compute resources for both training and inference. This is by design, as transformers trained with more parameters or data are demonstrably more capable than their slimmer predecessors, often by a significant margin. Still, a growing body of work suggests that transformer-based models and neural networks more generally do not require all fitted parameters to retain their learned hypothesis. While it seems helpful to be massively over-parameterized at train time, it's well known that these models can be drastically pruned before inference. Neural networks can often have well over 90% of their weights removed without any significant degradation in performance. The discovery of this phenomenon bolstered interest around the relationship between generalization and over-parameterization, and spawned research in developing pruning strategies that lend themselves to efficient model inference. This paper presents a surprising finding that careful pruning done at specific layers of transformer models can produce significant boosts in performance on some tasks. We describe layer-selective rank reduction, LASER, an intervention that removes higher-order components of learned weight matrices as identified by singular value decomposition, the Swiss Army knife of linear algebra. This reduction is performed in specific weight matrices and layers of the transformer model. In line with previous work, we find that many such matrices can be significantly reduced, and that performance degradation is often not observed until well over 90% of the components are entirely removed. However, unlike what is found in previous work, we find that these reductions can produce drastic improvements in accuracy as measured by various well-studied reasoning benchmarks in NLP. Even better, this discovery appears not to be limited to natural language, with performance gains also found in reinforcement learning. This paper analyzes the relationship between the model's training data and samples that benefit from LASER. We find that improvements in the model's performance predominantly come on information less frequently present in the model's training dataset, suggesting that LASER offers a kind of denoising procedure that makes weakly learned facts accessible. We separately observe that LASER affords increased robustness to paraphrases on previously correct questions. Additionally, we attempt to reason about what is being stored in high-order components, such that their removal boosts performance. For questions correctly answered only after LASER, the absence of intervention In the absence of interventions, the original model predominantly responds with high-frequency words such as the, of, etc. Generations that are not even the same semantic type as the correct answer. However, after some amount of rank reduction, the model's answer flips to be correct. To understand this, we look at what the remaining components encode on their own. We approximate the weight matrix using only its higher order singular vectors. We find that these components describe either a different response at the same semantic category as the correct answer or generic high-frequency words. Seemingly, when the noisy high-order components are combined with the low-order components, their conflicting responses produce a sort of average answer, which is likely to be incorrect. Figure 1 visualizes the transformer architecture and the procedure followed by laser. Here, the weight matrix of a multi-layer perceptron, MLP, at a specific layer is replaced with its low-rank approximation. Would you like to take this, Kai?
Figure 1?
Yes.
Okay, so top left, replace weights in specific layers with its low rank approximation, WLR. Now on the left, you'll see words going through different layers. Now this diagram is unnecessarily complex, but basically you have text, it's linearized, then it goes through self-attention, then it's added with the residual, then it's sent to an MLP that has a linear, a non-linear activation, a linear, then another pointwise addition. Then after that you have the layer L, which is the low rank approximation, where you have a linear layer, a pointwise addition, a linear layer, non-linear activation, and a pointwise addition. And then it keeps going for every layer. So basically what the red means is that you have a red weight. This weight is transformed into L. Then we take the low rank approximation of the weight, which equals U sigma VT. And the description says, a laser replaces the specific weight matrix W of the transformer model by its rank K approximation, LWR, and observes the changes in the model's behavior. We find that this rank approximation, especially for MLP weights in the later layers of the model, often offers surprising benefits to model performance.
Thank you, Kai. So, I have to say this reminds me of kind of the pruning that happens to people with memory recall consolidation and dreaming. In that we aren't always learning a full copy of our experience, but rather we learn an approximation of it. We recover an approximation of it. And that's a total guess, but it feels plausible to me. Okay, related work. To our knowledge, this paper is the first to identify that carefully selected rank reductions can boost transformer performance. Still, there's a wide array of works that study related questions, including how facts are stored in LLMs, and how to best compress neural networks. How facts are stored. Studies probing model representations for the presence of selected properties of entities show that models store factual information across different layers, and Layer 2023 shows that model robustness to distributional shift can be improved by fine-tuning selected layers. However, there's conflicting evidence on how this information is organized and used in constructing answers in large language models. Some theories posit that information about different entities is locally stored as two-layer key-value memory in MLP sections of transformer models, which are thereafter copied through later layers by the self-attention modules. Meng 2023 proposes a procedure to trace and edit local entity-specific information mapped to distinct impossible outputs, supporting the locality theory. These theories are further supported by the phenomena of early exiting, where the representation at an intermediate layer can be directly used with the terminal head of the model to correctly generate an output. In contrast, Hassett 2023 has observed that information about some of the same entities or entity relations can be modified by editing a variety of layers in the model architecture, and therefore that facts are stored across layers in a fragmented fashion. This paper makes no specific claims regarding locality, but rather demonstrates that higher order components of a weight matrix can introduce noise in decision making, and considering only lower order components may make correct answers accessible. Model compression. Neural network pruning methods have found that models could significantly be pruned, often removing over 90% of parameters with very little drop in accuracy, significantly reducing the storage requirements of the model. There have also been approaches that prune these models in a structured manner to facilitate improvements in inference time. The existence of sparse subnetworks has been found to be true for convolutional, fully connected, and transformer models. While Zhen et al. 2022 find that model generalization can be improved by pruning and then refitting parameters, generalization improvements are only observed upon model retraining. To our knowledge, model pruning techniques have always been done, there's a word missing, a unilateral reduction across all parameters without targeting any specific layers, leading to predictive performance either stay fixed or decreasing. In this work, however, we find that the effective reduction in accuracy is non-uniform across different layer types, and a model's generalization can be improved by selective pruning alone. No additional training is necessary. Roughly, we find that the performance degradation can be produced by rank reducing early layers, while significant performance benefits are typically available by pruning later layers. Low rank approximations of weight matrices. Most pruning methods reduce parameters in order of their absolute magnitude. Franking, Carbon 2018. An alternative approach, however, is to reduce the rank of its constituent weight matrices, keeping the top K components found by singular value decomposition. While matrices of neural models, including transformer models, have been found to be well approximated using this approach, where markedly reduced versions of the model can preserve its behavior, research has shown that performance eventually declines as the severity of the intervention increases. Note that these reductions are typically done unilaterally, removing the same number of components in every weight matrix in the model. In contrast to these findings, we show that a targeted rank reduction, even affecting just a single weight matrix, can offer benefits to the predictive accuracy of transformers. Model distillation and low rank training. Bowen and Karuna 2014 and Hinton 2015 have trained smaller networks to mimic the behavior of larger networks, suggesting that neural networks might be significantly over-parameterized and can be replaced with leaner alternatives. To our knowledge, no report of an improvement in the model's predictions as a consequence of this procedure has been shown. Yang et al. 2020 have enforced low rankness of weight matrices for the purpose of memory efficiency, but the resulting models fail to achieve performance equivalent to their over-parameterized counterparts. The results suggest that over-parameterization is helpful for the identification of well-generalizing parameters by stochastic gradient descent. This is exciting. Preliminaries. Here we review basic notation and describe the core components of our study. That's the notation. We use R to denote real numbers, N to denote natural numbers, small letters such as V as an element in RD to denote a d-dimensional vector, and capital letters such as W, an element in Rm times N to denote a matrix of size M times N. We use vertical bar V sub 2 to denote the Euclidean norm of a vector V, and vertical bar W sub 2 to denote the spectral norm of a matrix W. Do you know what a spectral norm is?
Do you?
No.
Spectral norm. The maximum singular value of a matrix.
So it's the square root of the maximum eigenvalue also.
I'm pretty sure that's the same thing.
Of course it is. Okay. We use N to denote the set 1 to 2N. We will use rank W to denote the rank of a matrix W, and sigma down arrow I, W, to denote its ith largest singular value. Transformer architecture. We provide a concise description of vanilla transformer architecture that is relevant to our analysis. A transformer architecture can be thought of as L layers of transformer blocks. The Lth block maps a sequence of T-length vector sequences, H sub 1, L minus 1, all the way through to H sub terminal T, L minus 1, to another T-length vector sequence, H sub 1 for L, all the way through to H sub terminal T to L, while all vectors are d-dimensional. This transformation is accomplished using two sequential steps, a self-attention mechanism to mix information across time steps, and a feed-forward network to process information within each time step. We describe a basic version of these transformations for a fixed Lth layer and drop the superscript L minus 1 for clarity. A single head self-attention mechanism first maps each vector H sub I to a query vector Q sub I, which equals W sub Q times H sub I. A key vector K sub I equals W sub K times H sub I, and a value vector V sub I equals W sub V times H sub I, where V sub Q, W sub Q, W sub K, and W sub V are matrices within RD times D, layer-specific weights matrices. We then compute the attention probabilities. Probability of J given I equals, I won't do the equation, for every I and J and T. These are used to compute the attention vector Z, which is the sum from J equals 1 to T of the probability of J given I for times V sub J. A K-head self-attention computes a set of K-attention vectors by using different linear transformations for key, query, and value, and then concatenates these attention vectors. These K-separate linear transformations for key, query, and value can all be absorbed into their respective matrices, W sub Q in R D times dk, W sub K in R D times dk, and W sub V in R D times dk. Finally, the self-attention mechanism outputs U sub I equals Z sub I times weight at 0 plus h1 using a projection matrix W at 0 in R dk times d. The feed-forward step applies a two-layer, multi-layer perceptron MLP phi in RD, which maps to RD to each vector U sub I in RD separately. The multi-layer perceptron typically has a ReLU or GeLU activation function, and in submodels such as llama, the bias of these linear layers is set to 0. We denote the weight matrices with first and second linear layers of this MLP by U sub in and U sub out, respectively. The output of this L transformer block is then given by H sub I for L equals phi of U sub I plus U sub I. In summary, a transformer architecture has the following weight matrices: W sub Q, K, V, O, U in, and U out for each layer. In addition to the embedding matrix for embedding input tokens, a projection weight matrix applied after the final layer before taking softmax, and all weight matrices associated with layer normalization. In our work, we focus primarily on the weight matrices in W and intervene by modifying them. Any questions on that?
Negative.
Okay. Rank R approximation and singular value decomposition. Given a matrix W in Rm times n and R in n, a rank R approximation problem requires finding a matrix W hat that minimizes the spectral norm of W minus W hat in 2 and satisfies rank W hat is less than equal to R. That's a big hat. Both of them, not the little hat. Eckert-Young-Mirsky theorem provides an optimal solution of this problem using singular value decomposition. Eckert and Young, 1936. Formally, a singular value decomposition of a matrix W is given by W equals U times the sum of the V transpose, where U equals U sub 1 all the way through to U sub M, which is an element in Rm times M, basis of Rm and Rn respectively, and V equals V sub 1 all the way through to V sub n, where R is an element in Rn times n, and sigma equals Rm times n. So we've got three matrices: U, which has order m, V, which has order n, and sigma, which is order m times n. The column vectors of U and V constitute an orthonormal basis of Rm and Rn respectively, and sigma is a diagonal matrix whose diagonal entries are given by the singular values of W in descending order. One can also express the singular value decomposition of W as W equals the sum from I equals 1, the minimum of M and N, times the sigma down arrow I, W, for times U sub I, E sub I transpose. According to Eckert-Young-Mirsky theorem, the matrix W hat equals the sum from I equals 1 to R of the sigma down arrow I times 4W times UI times VI transpose is an optimal solution to the rank R approximation problem for any given desired rank R less than equal to min M and N. In this work, we will use the word higher order components to refer to the entries in the singular value decomposition corresponding to their components with smaller singular values. These components are removed by laser. The term lower order components are used to refer to singular vectors corresponding to large singular values. These components are kept in a low rank approximation of the matrix. So this doesn't sound hard to compute. Figure 2. Because if they have the matrix W hat, then all they need to do is just use the lower portion of the diagonal. The effect of rank reduction across layer types is not uniform. This is figure 2. Here we show the effect of rank reduction for GPT-J as studied by the counterfact dataset. The dashed line is the unmodified network's loss for GPT-J as studied in attention layers key query value out matrices. While it is clear matrices could be significantly rank reduced without damaging the learned hypothesis, there is very little performance increase. However, for the multi-layer perceptron layers, rank reduction goes from uniformly harming to improving the model's performance around at layer 20. And so the MLP matrices are the two on the right on the lower row, and each of them show a decline in loss after layer 20. And for the output matrix, the decline in loss at layer 20 goes from a loss of 5.8 down to a loss of 5.4. The input matrix goes from a loss of 6 down to 5. And none of the other layers have what I would consider to be a pattern that is usable. The loss seems to be noisy around the median, and the intervention is not significant. If they do this reduction at an earlier layer in the matrix, that is between 0 and 5, the loss degrades significantly, about as much as the improvement. It degrades more than the improvement. This suggests to me that this technique might be used on transformer models which have many, many more layers than this without a significant impact. In fact, it might improve the response of transformer models with a lot more layers. And if transformers weren't so hecking expensive to train, I'd immediately suggest training a transformer model with 100 layers to see if this is true. Anyway, or even 50 for that matter. Are you taking notes, Kai?
I am.
Okay. Layer-selective rank reduction, laser. In this section, we will formally describe the laser intervention. A single-step laser intervention is defined by three quantities, tau, L, and P, consisting of a parameter type tau, layer L, and rank reduction P. These values together describe which matrix will be placed by their low rank approximation and how severe the approximation will be. The parameter type categorizes the matrix type in which we will intervene. We focus on the matrices in W, which consist of the matrices in the MLP and attention layers. The layer number described, the layers at which we intervene. The first layer is indexed from 0. For example, the llama 2 has 32 layers, and so L goes from 0 to 31. Finally, P in 0 and 1 describes what fraction of the maximum rank should be preserved upon doing its low rank approximation. And P goes from including 0 to not including 1. For example, tau equals U in R D times D. Then the maximum rank of this matrix is D. We replace it with the rank P times, I think that's what it says, P times D approximation. Figure 1 shows an example of laser. In this figure we have T equals UN and L equals big L, indicating that we update the weight matrix in the first layer of the MLP in the transformer block of the Lth layer. The other parameter not shown in the figure controls the K in the rank K approximation. Laser throttles the flow of certain information in the network, which surprisingly can produce significant performance benefits. These interventions can also be easily composed. We apply a set of interventions, tau sub 1, L sub 1, P sub 1, in I equals 1 to M in any order. The laser approach is to simply search over interventions of this type and to exercise the modification that offers the greatest benefit. There are many other ways which one can combine these interventions, however, and we defer this to a future work. Experiments. This section studies the consequences of laser throughout various layers of the transformer architecture. We first perform a motivating analysis of counterfact, question answering dataset in conjunction with a pre-trained GPT-J model, and investigate the performance of the model and its variability as we search over potential interventions. I wonder if this is what they did for GPT-4. Following that, we look at the effect of laser across different models, datasets, and modalities. GPT-J, counterfact, and pile. We use the GPT-J model with 27 layers and 6 billion parameters pre-trained on the pile dataset. The first part of our analysis focuses on GPT-J, largely because its training data is publicly available. We evaluate the model's behavior on the counterfact dataset, which consists of samples organized as subject relation Ansel tuples and 3 paraphrase prompts for each question. For example, Daniel Deroux, mother tongue French. I'm going to skip section 5.1. And go to figure 2. Figure 3, sorry. Which data points benefit from laser? We analyze how frequently in the training data corrected facts occur. GPT-J is an ideal testbed for such analysis since its training data, detrain, in the pile dataset is publicly available. For GPT-J trained on counterfact, DQA, we retrieve all the data points in detrain that contain a mention of both the entity of interest and the answer that corresponds to each sample in DQA. B, a plot depicting the cumulative top 10 accuracy of the model on all data points that occur in the training data less than or equal to the frequency indicated on the x-axis. Here we show accuracy with and without laser, and accuracy is improved on every item that appears. This frequency looks like less than 100 in the data set. C, the largest boost in performance occurs for low frequency samples. The bar chart displays the amount of boost offered by laser for data binned by the frequency with which the corresponding facts occur in detrain. Maximum improvements in accuracy are from data points that have less frequent occurrences in the data set. So a big over here. And smaller later. Composing reductions across layers. We find that even further improvements in the model's performance can be made by performing different amounts of rank reduction across several layers. This is done by greedily searching over tau LP, starting from the largest L and smallest P. To speed things up, here we do the search only over MLP layers, as this is where the largest improvements are typically found. Consistent with other experiments, the search is done on a validation set, and the results are reported on the test set. On counterfact, the 0-1 accuracy of the base GPT-J model is 13.1%. After doing the best single-step laser, the model's accuracy improved to 24%. OMG. Performing laser across different layers improves the top 10 accuracy to 29.2%, a 5.2 absolute improvement in accuracy over performing laser on a single layer, and more than a doubling of accuracy from the base. The results of this combinatorial search across different LMP values can be seen in Figure 4, where it appears that even as late as, I'll say, there was a continuing improvement. After that, it flattens out significantly. Okay. 5.11, which facts in the data set are recovered by rank reduction? To understand this phenomenon, we looked at the questions correctly answered after laser and the effect of how often the information associated with the question appears in the training data. For every data point and counterfact, we retrieve all the examples in pile that contain both mention of both entity and the answer. We then compute how often information associated with each evaluation question appears in the training data. We find that facts recovered on rank reduction are most likely to be infrequently present in the data. Figure 3. Here, originally correct, describes samples that are correctly classified even without any intervention. Answer corrected refers to questions the model gets correct only after intervening with laser. Figure 5. A on the left, laser approximates learned matrices by their lower rank or their lower order components. And A is average correct, going down on the Y. And the one on the left shows that the correct answers are in the upper right of the left matrix, and wrong answers are in the lower right of the left of the right matrix. In both cases, the outer portion of the matrices have average answers, and the corners have either the correct or the wrong answer. To understand what these higher order components encode, we approximate the learned weight matrix with the higher order components instead. We find that these higher order components sometimes encode the correct semantic type of the answer, but the incorrect response. B. And B is the graph on the right. Analytically, computing the semantic similarity cosine distance between the true answer and the answer generated by the bottom k% of the singular vectors shows that on average the answer computed by the higher order components is more similar to the real answer. And C at the bottom are some examples from the data set and the corresponding answers computed by the top fraction and bottom fraction of the components. Saeed Akbar Misra is originally from Mumbai, and the bottom is Pakistan. I don't know the answer to that. Manuel DeVoe's profession is an actor-teacher. I'm assuming actor. I don't know the answers to these. The twin city of Wellington is Sydney or off I would think. Headquarters of More Music is located in Berlin, not that. Abba Eban was employed in Jerusalem. The top answers are better. Okay. I've won 2. What are higher order components storing? We saw above how retaining the lower order components improved model performance on the task of open-ended question answering. We find that for the task of question answering, improvements often come on questions whose answers are supported by less frequently occurring data in the training set. While it's clear that eliminating the higher order components denoises the model and helps recover hidden, less frequent information, it's not clear what the higher order components are representing, such that their removal improves performance. This section studies this question using the counterfeit dataset in GPT-J. To understand what higher order components are representing, we approximate the final weight matrix using its higher order components as opposed to approximating it using its lower order components as done by laser, shown in figure 5a. Following this, we analyze how the model's behavior changes on data points that GPT-J originally gets incorrect, but are flipped to be correct upon performing laser. First, we note that when the original unmodified model does not answer these questions correctly, it often responds with common words such as a, the, of, and other highly frequent tokens. After performing laser, where we retain only the top K components, the model's answers to these questions flip from generic words to the correct entity. For the same data points, when we approximate the model by instead retaining the higher order components, we find that the model either predicts incorrect entities that are of the same semantic type as the correct answer, or high frequency tokens such as a, the, and of, as shown in figure 5c. However, as we systematically include the lower order components, the model's average changes to predicting frequent tokens. The model's output changes to predicting frequent tokens. To investigate the systematic degradation, we measure the average cosine similarity of the true answer with respect to the predicted answer when the matrix is approximated with different amounts of higher order components, as shown in figure 5b. The average cosine similarity between the predicted answers worsens, demonstrating this effect. We hypothesize that these matrices often encode multiple conflicting responses, and that when all components are used, they clash to produce a generic token. Removing the higher order components, which anecdotally appear to capture incorrect responses of the correct type, resolves this internal conflict and allows the model to respond accuracy. Oh. 5.2. How generally does this hold? Natural language understanding tasks.
Let's just skip this to the conclusion.
Okay. This paper describes laser, a phenomenon where performing a low-rank approximation of specific layer types at specific layers of a transformer block can improve the performance of LLMs on the task of question answering. We find this to be true across 5 different data sets and 3 different language models. Furthermore, the resulting laser reductions are extreme. The matrices are reduced at times to 99% of their original rank, which is much lower than their effective rank. That's Appendix C.1. However, despite extreme reductions, the performance of the model on tasks continues to improve. We also observe performance gains for a decision transformer in an embodied domain. We find that the largest improvements in the model accuracy correspond to information that is less common in the training data, and that laser jointly makes the model more robust to paraphrases of the questions. We further found that the higher order components of some of these matrices encode either high-frequency words or alternate answers of the same semantic type as the correct answer. These noisy high-order components can overpower the stable lower-order components and result in the model answering questions incorrectly. In these cases, performing laser acts as a denoising technique and reduces the internal conflicts in potential responses. Despite this analysis, the success of laser requires further study, learning 1. Why higher order components in weight matrices accumulate noisy answers in the course of training, 2. The effect of model architecture and other structural choices in the occurrence of this phenomena, and 3. Why this is specifically true for the later layers in the MLP is important not only for our understanding of the success of laser, but for understanding the behavior of large language models more generally. Oh, this is a good paper. They use Sokobin for the decision transformer domain. Extended analysis, C1. Are weight matrices already low rank? As seen in figure 7, we find that laser approximated matrices with their low rank approximations much beyond their effective rank. To study this, we computed the effective rank of the MLP matrices, which laser helps for GPT-J, using the method described by Roy and Verletti 2007. The plot shows that although matrices of the later layer have a lower effective rank than the earlier layers, the computed effective rank is significantly larger than the reduction percentage until which laser helps. C2, how much reduction is too much? We see that for many of the matrices in cases where reduction helps, with increasing amounts of rank reduction, the model first monotonically improves before it starts to worsen, as seen in figure 8. The point to which it improves varies depending on layer type and layer number. However, monotonic improvement and worsening are observed consistently. What's the effect of removing the layer completely? We find that removing the layer completely can be better than retaining its matrix with full rank. However, it is observed to be worse than the model with the low rank approximation of the matrix. And this is figure 7, the effective rank of the matrices as described. We have on the y-axis from 2600 to 3800, with the orange one at the top being the MLP for the outweight, and the collection of lines at the bottom are the attention layers, and going from 0 through to 25. Does layer select the same layer for different tasks? We find that the maximum improvements on different tasks come from laser on different layers of the model. Figure 9 shows that for GPT-J on different tasks, the best performing models across tasks have reduced matrices in different layers. They measure perplexity on the pile. The improvement, the model's perplexity worsens slightly after applying laser. We do not yet fully understand what the worsening in perplexity of the model corresponds to, and leave this for further study. And final layer search results. These values are obtained by reporting the optimal laser parameters that maximize the validation accuracy. The results show that the optimal improvements in the model typically come from later layers in the transformer model, typically from reducing the MLP input matrix. Note that L equals 0 denotes that the intervention is done on the first layer. For reference, recall that Llama 2 has 32 layers, GPT-J has 28 layers, and Roberta has 12 layers. The magnitude of reduction are also quite large, with the rank at times being reduced to 1% of the original matrices rank. And they tried alternate pruning methods. And so the percentage reduction degrades after about 99.5%. 99.95%. Table 3, final search results. I'm going to skip that. Figure 9, the largest benefit of laser comes from reduction on different layer numbers. Let's see, counterfact, fever, hot pot, and bias and bios. Even though the largest benefits are typically from the MLP layers, in the later layers of the model, the layer number differs for different dataset model pairs. Implementation details.
I think that's it. There's nothing else.
Okay.
Honestly, this is a 5 out of 5.
Right?
5 out of 10.
5 out of 5. Yeah. And there's code.
But there's no like easy way to implement this. They don't have algorithmic pseudocode, and the formulas are all over the place. The diagram also doesn't exist. The diagram that they show, figure 1 is not, like, that's not an implementation of laser. It's showing it when it should be used, yes, but not how it's used. So what do you think?
I'm looking at the code. I think that it should be possible to implement this.
Obviously.
Where the hell is the thing? So this is actually decent code for attempting to be reproducible. But I don't know where the algorithm is. It's getting close. There it is. So each of the different models has a different laser.
That's very low IQ.
They're researchers. They've already given us so much.
Not really. If you don't
the idea is really valuable.
No, not at all. I could give you an idea on how to make $1 billion. Is the $1 billion created as soon as I give you the idea? No.
The work has to happen next. I will say that $1 billion ideas are not rare. It's all about getting the stuff done. Thank you for selecting this paper, Kai.
Yeah.
That was exciting. I'm